Welcome to PLCs for Beginners. This course is recommended as a prerequisite to more advanced training, but it can also be helpful if you simply want to learn basic concepts. This course covers the following topics: PLC overview, PLC hardware, numbers, codes, and data types, inputs and outputs, SEMATIC S7 modular PLCs, PLC programming concepts, basic ladder diagram programming, and basic function block diagram programming. The focus of this course is on PLC concepts and terminology and not implementation knowledge and skills. This chapter covers the following topics: PLC overview, PLC hardware, and numbers, codes, and data types. Completion of this chapter will help you learn important PLC terms and develop an understanding of basic PLC concepts. Most factories contain dozens or even hundreds of machines, from the very simple to the complex. Some are still operated and controlled only by skilled workers. However, most complex machines rely on programmable logic controllers, PLCs for short. A PLC is an industrial computer that is used to control machines and processes. PLCs differ from office computers in the types of tasks they perform and the hardware and software they require. While the specific applications vary widely, all PLCs get inputs from switches and sensors, make decisions based on a stored program, and control outputs to automate machines and processes. Before PLCs were invented, machines were often controlled by electromechanical devices with complex wiring. This approach is called hardwired control. Hardwired control is still used for simple tasks, but for larger applications it is difficult to design, install, and maintain. Because tasks performed by PLCs are controlled by software and internally stored values, use of PLCs offers exceptional flexibility. As a result, PLCs are now used to run almost any industrial application, and almost every new machine that comes into a factory has a PLC controlling it. Consequently, many industrial jobs require knowledge of PLCs. The very first PLCs were designed for use in the automotive industry in the late 1960s. Prior to that time, control of an auto assembly line relied heavily on electromechanical relays, contactors, timers, and related devices. Every year, as design changes were made to different car models, these circuits had to be rewired. Rewiring circuits was a complicated and time-consuming task, and even when the relays performed well initially, the wear on all those physical contacts resulted in costly maintenance. Additionally, as manufacturing processes became more and more complicated, more relay circuits were needed. This resulted in even greater cost and complexity. Because the hardwired circuits replaced by PLCs used control circuit diagrams referred to as ladder diagrams, early PLCs used ladder diagram software programs, sometimes referred to as ladder logic, to make it easier for someone familiar with control circuits to program a PLC. Unfortunately, every manufacturer had its own version of ladder diagram programming. This variation in programming grew as PLCs were developed to handle a wider range of tasks. Today, most PLCs can still use ladder diagram programming, but the IEC 61131 International Standard now defines this programming language. This same standard also defines other types of programming languages available for PLCs so that they can be used for the most complex applications. In addition, even a small PLC can easily outperform hardwired electromechanical circuits. Most PLCs have a modular structure. Some PLCs have a block-type modular structure, but the majority have a traditional modular structure. Despite their variation in appearance, modular PLCs have a similar organization which includes the following components. The central processing unit, CPU, is the brains of the PLC. The CPU stores and runs the user program. The input-output system, often referred to as the I/O system, includes modules with I/O channels that connect to input devices such as switches and sensors, and output devices that are controlled by the PLC. A programming device is used to load the program to the CPU memory. The programming device is usually an industrial personal computer with software that allows you to create and modify PLC programs. The programming device is only connected to the PLC when it is needed. Although not part of a PLC, one or more human-machine interfaces, HMIs, are often connected to a PLC to allow factory personnel to monitor or alter a machine or process. PLC I/O devices are sometimes the same as devices used in hardwired control circuits, but the relationship of these devices is determined by software referred to as the user program, which is stored in the CPU. This program is executed repetitively as part of a process referred to as a scan. After startup, a PLC scan includes the following sequence of operations. The PLC reads the statuses of input devices and records this information in its memory. The CPU executes the user program and changes internal memory values as needed. The CPU performs internal diagnostic and communication tasks. The CPU sends updated status information to output devices through the I/O system. This process is repeated continuously as long as the CPU is in the run mode. The time required for a scan depends on the capabilities of the CPU, the size of the user program, the number of I/Os, and the amount of communication required. However, because PLCs are very fast, a typical PLC scan is measured in milliseconds. This means that the PLC response time from reading an input to reacting by changing an output is also very fast. Input devices are usually switches or sensors that send electrical signals to the CPU through input channels on input signal modules. Similarly, output devices receive electrical signals from the CPU through output channels on output signal modules. These output devices are sometimes called actuators and are used to control a machine or process. PLCs have two broad categories of I/O, digital I/O and analog I/O. Digital I/O devices, also called discrete I/O devices, are either on or off and are connected to digital I/O channels. Analog I/O devices use variable voltage or current signals and are connected to analog I/O channels. Analog I/O is used in applications where variable quantities such as temperature, pressure, rate of flow, etc. are being controlled or monitored. The central processing unit, CPU, is the brains of a PLC. The CPU stores the user program, I/O status bits, and other data. It also repetitively executes the PLC scan as previously described. As part of this scanning process, the CPU receives input information from input channels and sends output information to output channels. Somatic S7-1200 CPUs have a small number of I/O channels in the same housing. Most of these CPUs also have the capability to connect to I/O signal modules for additional I/O channels. Most other Somatic PLCs have all I/O channels on I/O signal modules. Both S7-1200 and S7-1500 CPUs have one or more communication connections referred to as ports. A communication port is designed for a specific type of communications. When a different type of communications is required, or when additional communication ports are required, one or more communication modules are used. Digital input devices provide an on or off signal to a digital input signal module in response to an operator input or a change in condition in a machine or process. The input device may operate on direct current DC or alternating current AC, and the voltage and current level is dependent on the type of device. A digital input signal module converts this value to a low-level DC signal that represents the on or off condition of the input device. For each digital input device, the on or off signal is stored in the CPU. Analog input devices provide a variable voltage or current to an analog input signal module. This variable voltage or current represents a condition in a machine or process such as temperature, pressure, vibration, rate of flow, weight, fluid level, etc. An analog input signal module converts each current or voltage value to a low-level DC signal and sends it to the CPU. For each analog input device, the latest value received from the device is stored as a number in the CPU. Digital output devices are turned on or off by signals from digital output signal modules. For example, an indicator light on an operator panel may be turned on to indicate that a machine is running. Often, however, the digital output device is used to cause a change in a machine or process, such as starting or stopping a motor or pump. Analog output devices receive a variable voltage or current signal from an analog output signal module. For example, an analog meter on an operator panel could be used as an analog output device to show a condition in a machine or process. Often, however, an analog output device is used to control a machine or process. For example, analog outputs from a PLC could be used to control AC drives, which in turn control pumps that fill and drain a storage tank. Input and output devices are often used to interconnect panels with lights and switches to one or more PLCs so that operation and maintenance personnel can monitor and control a machine or process. Increasingly, human-machine interfaces, HMIs, are also used for similar purposes. HMI panels range in capability from simple keypad devices to panels with the ability to graphically display an entire process. An HMI can also be a mobile device that allows freedom of movement for operation or maintenance personnel. A programming device is often a personal computer, PC, with software that enables it to program a PLC. Often an industrialized PC is used so that it can function reliably in a factory environment. The programming device frequently has additional functionality depending upon the software used. For example, a programming device running Siemens Totally Integrated Automation Portal, TIA Portal, software is used in all phases of the design, operation, and maintenance of systems that include PLCs, HMIs, PCs, electronic drives, and related devices. There are multiple ways to program a PLC. At one time, PLC programming languages varied with the PLC manufacturer. In general, however, PLCs manufactured in recent years are programmed using a language defined in an international specification, IEC 61131. Two of the programming languages defined in this specification are ladder diagram, LAD, and function block diagram, FBD. A PLC is made up of hardware and software. Hardware is the part of a system that you can see, and software is the collection of computer programs that control what the hardware does. PLC hardware also connects to other hardware, such as input and output devices and human-machine interfaces, HMIs. Although not in the accompanying graphic, a programming device can also be considered as PLC hardware, but it is only connected to the PLC when needed. Because PLC applications vary in complexity, there is considerable variation in the appearance of PLC hardware. In a typical application, small and medium-sized PLCs are often used to control individual machines or manufacturing cells. These PLCs typically communicate via a network to one or more larger PLCs that collect data and coordinate the operation of some or all of the system. Additionally, because the needs of customers vary, Siemens Somatic PLCs are available as modular controllers, embedded controllers, or as PC-based controllers. Of these three categories, modular controllers are the most common and are the focus of this course. Somatic S7 modular PLCs include a variety of models. For example, S7-300 and S7-400 PLCs have been in service for many years. More recently, S7-1200 and S7-1500 PLCs have been introduced. Regardless of the model, Somatic S7 modular PLCs are optimized for control tasks and can be adapted to meet application requirements by adding modules. Typical PLC module types are CPU modules, power supply modules, signal modules, communication modules, and special purpose modules. PLC CPU modules all contain a microprocessor, which is an integrated circuit that runs the computer software, and memory circuits that store the user program and related data and may include a removable memory card. A CPU may also have an internal power supply that converts the supplied power to the filtered low-voltage DC needed by internal circuits. If the CPU does not have an internal power supply, a system power supply module is needed to provide power. CPUs typically have the following three operating modes. In the stop mode, the CPU is not executing the user program, and a new program can be downloaded to the CPU. In the startup mode, the CPU executes any startup logic if present. In the run mode, the CPU executes the PLC scan repeatedly. The specific mode the PLC is in at any given time depends on a software setting and whether or not a critical CPU error has occurred. In the event of a critical error, the CPU is designed to go into the stop mode. The current mode for S7-1200 and S7-1500 PLCs is shown by the CPU Run Stop LED. The current mode for S7-1500 PLCs is also shown on the CPU's integrated display. Modern PLCs use modules that have solid-state memory. The memory size for each type of memory is specified in bytes, with 1 byte equal to 8 consecutive binary bits. Because modern memory circuits can store a large number of bytes, the following metric unit prefixes are used to indicate memory size: kilo K, mega M, and giga G. There are a variety of solid-state memory types, but these are the most common types. Read-only memory, ROM, stores information developed by the PLC's manufacturer that cannot be changed. This type of memory is non-volatile, meaning that the information contained will not be lost in the event of a power failure. Erasable programmable read-only memory, EEPROM, is protected from unauthorized changes. EEPROM can be read from, but not easily changed. EEPROM storage is sometimes referred to as firmware. Modern firmware is often designed to be updated when required. This is also a non-volatile memory type. Random access memory, RAM, is also called read-write memory and is used for temporary storage of programs and data. RAM is volatile, meaning that information will be lost in the event of a power failure unless power to the circuits is backed up by a battery or charged capacitor. Flash memory is a type of electrically erasable programmable read-only memory, EEPROM. Flash memory is a non-volatile memory type that, among other things, is used for somatic memory cards. These cards are available in a range of sizes and can be used to store or transfer a PLC user program and associated data. PLC CPUs have a memory organization that defines the available storage for various types of information. PLCs of a specific model typically have a range of CPUs that vary in the amount of user memory available. Descriptions of user memory types vary from PLC to PLC, but the following user memory types are typical for somatic S7 PLCs. Load memory is non-volatile storage for the user program and related data. When a user program is downloaded to the CPU, it is first stored in the load memory area. This area is located either on a memory card or in the CPU and is maintained through a power loss. Work memory is volatile storage for some elements of the user program. The CPU copies these elements from load memory to work memory during program execution. This is volatile memory, so the information is lost when CPU power is lost, but is restored by the CPU when power resumes. Retentive memory is non-volatile storage for a limited amount of work memory information. Much of the data used by the user program is stored in data blocks in the program. However, CPUs have global memory areas that are accessible by the user program. These include input I and output Q process image tables and bit memory M. Some CPU modules have an integrated power supply for powering onboard circuits. However, some PLC models or configurations require a separate system power supply for this purpose. This system power supply converts the incoming power to filtered, regulated, low-voltage DC power. The system power is provided to a backplane that is common to multiple modules. Multiple system power supply types are typically available for a PLC model to match the input voltage, which may be DC or AC. System power supplies also have a power budget that defines the amount of power available for interconnected modules. A load power supply, also called a load current power supply, provides power to input and output devices as well as the related input and output circuits. In some cases, the load power supply also provides power to other PLC modules, including a system power supply module. The load power supply module, PM, for a Somatic S7 1500 PLC mounts on the same mounting rail as other S7 1500 modules. Siemens also offers a variety of C-top power supplies for use with a wide range of equipment. PLCs have a variety of signal module types. Each module has multiple I/O channels, and each I/O channel connects to one I/O device. The number of I/O channels on a module varies with the module type. Some modules have both inputs and output channels. Each input and output channel on a module has an LED that shows the status of that channel. One or more additional LEDs show the status of that module. Signal modules of various types are interspersed as needed throughout a system. Each module is configured at installation, and this configuration includes the assignment of a module address. This address, together with the module type, also identifies the location of image table status bits for the connected inputs and outputs. As a result of this configuration, a discrete input, DI, or discrete output, DQ, is associated with a specific image table status bit, and this input and output status information is available to the user program. Because each analog input or output must represent any value in a range of values, each analog input, AI, or analog output, AQ, is associated with a word, 16 bits of memory. PLC At one time, PLC communications primarily used networks designed by equipment manufacturers for their own equipment. As more control devices with built-in computers were developed, the need for common approaches for communications emerged. This led to development of a variety of field buses by industry associations. A field bus is an industrial network used for distributed control. One example of a field bus is Profibus DP, the leading field bus standard, which was developed by Profibus and Profinet International PI. With the growth in information technology, IT, the need for control systems to communicate with IT systems increased. IT systems often communicate via Ethernet local area networks, LANs. However, the original form of Ethernet was not adequate for factory communication, so industrial Ethernet was developed. Profinet, which was also developed by PI, is the leading industrial Ethernet standard. A PLC CPU often has one or more ports for a specific type of network communications. For example, S7-1200 and S7-1500 CPUs have at least one Profinet port. When additional network ports are required or when a different type of connection is needed, communication modules are added to the configuration. PLCs are very fast and have many types of signal modules, but some tasks require special purpose modules. Many of these modules are designed for closed-loop control applications, which involve controlling a process or machine in response to a feedback signal from a sensor. A closed loop may require a special purpose module because of the type of sensor, control device, or algorithm used. A control algorithm is a set of rules or calculations that define the control process. For example, the proportional integral derivative PID control used in many applications uses a control algorithm. In addition to closed-loop control applications, PLCs use special purpose modules for counting or generation of high-frequency pulses. S7-1200 PLCs have integrated technologies for high-speed counting, measuring, proportioning, open-loop stepper motor control, and PID control, reducing the need for special purpose modules. S7-1500 PLCs also have technology modules for high-speed counting and measurement applications. PLCs connect to a wide variety of devices, some of which use variable voltage and current values. Internally, however, PLCs use signals that are either off or on. These off and on signals correspond to binary values 0 and 1. A binary 0, also called logic 0, can be used to indicate that an input or output is off, and a binary 1, also called a logic 1, can be used to indicate that an input or output is on. Consecutive binary bits are also grouped in lengths ranging from a byte to a double word to represent various types of information. For example, a group of consecutive bits, sometimes called a bit string, may represent a numerical value in various number systems such as binary, octal, decimal, and hexadecimal. Because a bit string can represent many things, it must be assigned a data type so that a PLC can properly interpret the information. The decimal number system is sometimes called base 10, and every position in a decimal number represents a power of 10. The available numbers, digits, for each position range from 0 to 9, and the numerical value of a position is determined by multiplying the position digit by the power of 10 for that position. The total numerical value for a decimal number is found by adding the numerical values for all positions. While binary, octal, and hexadecimal numbers may at first seem confusing, they follow the same concepts as decimal numbers, except that the number base and available characters are different. The binary number system has a base of 2 and uses only 2 characters, 1 and 0. Each position is called a bit and is associated with a power of 2 based on where it is in the number. The further to the left a bit is in a binary number, the higher the power of 2. The number on the far left-hand side is referred to as the most significant bit, or MSB, and the number on the far right-hand side is referred to as the least significant bit, or LSB. A 1 is placed in a position if that power of 2 is used in the number, otherwise a 0 is placed in a position. The number of bits used to represent numbers varies, but in the example shown, an 8-bit binary number, also called a byte, is used. When a PLC does a calculation, it does not convert a binary number to decimal to make the calculation. However, it is useful to understand how to convert a binary number to decimal. Fortunately, the process of converting a binary number to an equal decimal value is as simple as adding the equivalent decimal value for each position in a binary number where a 1 is shown. Positions with a 0 do not add to the number value. The process of converting a decimal number to a binary number is easy to do by repeatedly dividing the decimal number by 2 and placing the remainder in the appropriate position in the binary number. For the example shown, the first remainder, 0, is placed in the 1's column. The next remainder, 1, is placed in the 2's column. The process continues as shown with the last remainder of 1 placed in the 128's column. This shows that 11001110 in binary is equal to 206 in decimal. Octal is another number system used with PLCs. The octal number system has a base of 8 and uses characters 0 through 7. Each position is associated with a power of 8 based on where it is in the number. The further to the left a position is, the higher the power of 8. The process of converting an octal number to an equal decimal value is as simple as adding the equivalent decimal value for each position in the octal number. Although you will not frequently have to convert decimal to octal to use a PLC, it is easy to do this conversion by repeatedly dividing the decimal number by 8 and placing the remainder in the appropriate position in the octal number. For the example shown, the first remainder, 1, is placed in the 1's column. The next remainder, 3, is placed in the 8's column. 8 does not divide into 4, so that leaves a remainder of 4 in the 64's column. This shows that 281 in decimal is equal to 431 in octal. The real value of octal comes from its relationship with binary. While a PLC can easily use binary numbers, sometimes it is convenient for humans to see equivalent binary values in octal because octal numbers require fewer place values to represent a number. If you know the equivalent binary number for each of the octal characters, 0 through 7, you can easily convert an octal number of any length to the equivalent binary number. The hexadecimal number system has a base of 16. This means that 16 values must be represented for each position in a hexadecimal number. This is done by using the numbers 0 through 9 to represent the first 10 values and the letters A through F to represent the remaining 6 values. Each position in a hexadecimal number is associated with a power of 16 based on where it is in the number. The further to the left a position is, the higher the power of 16. The process of converting a hexadecimal number to an equal decimal value is as simple as adding the equivalent decimal value for each position in the hexadecimal number. Although you will not frequently have to convert decimal to hexadecimal to use a PLC, it is easy to do this conversion by repeatedly dividing the decimal number by 16 and placing the remainder in the appropriate position in the hexadecimal number. For the example shown, the first remainder of 15, represented by F in hexadecimal, is placed in the ones column. The next remainder of 3 is placed in the 16s column. 16 does not divide into 13, so you are left with a remainder of 13 represented by D in hexadecimal in the 256s column. This shows that D3F in hexadecimal is equal to 3,391 in decimal. The real value of hexadecimal comes from its relationship with binary. While a PLC can easily use binary numbers, sometimes it's convenient for humans to see equivalent binary values in hexadecimal because hexadecimal numbers require fewer place values to represent a number. If you know the equivalent binary number for each of the hexadecimal characters 0 through F, you can easily convert a hexadecimal number of any length to the equivalent binary number. PLCs use a variety of input and output device codes. Binary coded decimal, BCD, is the most common of these codes. BCD is not a number system, but is used by some input and display devices because it allows people to input or see values in decimal. Internal to the PLC, BCD values must be converted to binary numbers that the PLC can use. An example of a BCD device is a type of 4-digit thumbwheel switch. Each thumbwheel digit controls 4 PLC inputs, so a 4-digit thumbwheel uses 16 digital inputs. Each thumbwheel digit represents decimal values 0 through 9. An integer is a whole number. There are a variety of ways to show an integer, and the integer types available vary with the PLC model. As the accompanying graphic shows, there are 8 integer types available for Somatic S7-1500 PLCs, 4 unsigned integer types, and 4 signed integer types. Both unsigned and signed integers are available to meet the requirements of various types of instructions in a PLC program. Integer types of varying length are available so that only the amount of memory needed is used. In other words, why use 64 bits to store a number when only 8 or 16 bits are required? When a signed integer is stored, bit patterns beginning with 0 are used to store 0 and all the positive values, and bit patterns beginning with 1 are used to store all the negative values. Negative values are stored in 2's complement form, which means that the pattern of bits for a negative binary number is determined by inverting all the bits in the equivalent positive binary value and then adding 1. 2's complement is used to store negative values in PLCs because it simplifies math processes. The accompanying graphic shows the range of binary numbers and their equivalent decimal values that can be stored as a signed short integer. PLCs work with real numbers, also called floating point numbers, which are expressed in scientific notation. To convert a number to scientific notation, move the decimal point to the left or right to create a mantissa that is greater than or equal to 1 but less than 10. Then multiply the mantissa by a power of 10 to compensate for the decimal point movement. Real numbers are often displayed as a mantissa followed by E and then an exponent. In the 32-bit format, the first bit represents the sign associated with the mantissa. A 1 represents a negative sign. The next 8 bits represent the exponent, which can be negative or positive. The remaining 23 bits represent the mantissa. There is a similar 64-bit format. Siemens Somatic PLCs can use 32-bit real numbers. Siemens Somatic S7-1200 and S7-1500 PLCs can also use 64-bit long real numbers. Binary bits can be used independently or as a group. When used as a group, they are used to represent numerical values as well as other types of data. In order to know how a bit string will be interpreted by a PLC, you must know the data type. which is the PLC's description of the data. PLC data types of various lengths are specified for binary numbers, integers, floating point numbers, date and time, characters, parameters, system data, and other types of data. Because the number of data types has increased over time, not all data types are available for all SIMATIC PLCs. The accompanying graphic shows the binary number, integer, and real number data types available for some of these PLCs. This chapter has provided you with an overview of PLCs, PLC hardware, and numbers, codes, and data types used by PLCs. The concepts and terminology discussed in this chapter will be useful to you in the remaining chapters of this course.